Today, we're diving into a realm where that's the everyday reality. We're talking about particles that are fundamental to our universe, yet almost utterly indifferent to interacting with anything else. Imagine trying to feel a breeze from a ghost that gives you a sense of the challenge, and the ultimate poster child for these elusive entities within the standard model. Neutrinos.
Absolutely. Neutrinos are the ninjas of the particle world. They are not just a theory. We detect them constantly. Trillions of them passing through you right now without you noticing a thing.
Right now, wow.
But when it comes to actually studying them in detail, that's where things get really interesting. It demands incredible ingenuity.
Exactly. So in this deep dive, we're zeroing in on these fascinating neutrinos. We're going to unpack what makes them such masters of this cosmic hide-and-seek.
Right.
And explore the remarkably clever ways scientists have devised to build detectors that can actually register these nearly invisible particles.
Yeah, it's quite a story.
Think of it as a scientific detective story where our suspects are some of the most subtle components of reality. Our mission today is simple: to give you a clear understanding of why particles like neutrinos are so elusive, and to really appreciate the sheer inventive power that goes into their study.
And this quest has a significant history. The neutrino was first proposed way back in 1930 by Wolfgang Pauli.
Pauli, right.
He essentially conjured it up to explain a puzzle in beta decay, a type of radioactive decay where energy seemed to vanish.
Like missing energy.
Exactly. But it wasn't until 1956, a full 26 years later, that the first direct detection occurred.
26 years.
That long gap right at the beginning tells you everything about their elusive nature.
Wow, 26 years. To propose something exists and then wait more than 2 decades to find proof. So what are the fundamental reasons these neutrinos are such avoidance experts? Okay, let's unpack this a bit.
It boils down to a few key fundamental properties. First, they have no electric charge.
No charge, okay.
This might sound simple, but its implications are profound. Because they're neutral, they don't interact via the electromagnetic force. They aren't affected by electric or magnetic fields, they don't ionize matter, and they don't directly interact with light. Photons just pass straight through them.
So light just ignores them.
Pretty much.
Yeah.
This immediately rules out a huge range of standard particle detection methods.
So no electrical signals, no sparks, no light flashes when they pass by. Got it. What else makes them so difficult to pin down?
Secondly, they have an incredibly small mass. For a long time, we actually thought they were massless, like photons.
Oh.
But we now know they possess a tiny non-zero mass, though it's still millions of times smaller than that of the electron, for example.
Millions of times smaller.
Tiny. And this minuscule mass contributes to the fact that their primary interactions are through the weak nuclear force.
The weak force, huh? Sounds, well, weak.
Precisely. That's the third crucial property. Neutrinos interact almost exclusively via the weak nuclear force, and also through gravity, although gravity's influence is negligible at the particle level.
Okay.
Now, the weak force lives up to its name. It's intrinsically much weaker than the electromagnetic or strong nuclear forces.
Much weaker.
And it operates over incredibly short distances, much smaller than the nucleus of an atom.
Wow.
Think of the weak force as the shy sibling of the other fundamental forces, much fainter and only really noticeable up close.
So they need to get incredibly close to something to even have a chance of interacting, and even then it's a long shot.
Exactly, which leads to the fourth point. Their incredibly tiny interaction cross-section.
Cross-section, that's like the target size.
Sort of, yeah.
Yeah.
It's essentially a measure of the probability that one particle will interact with another. For neutrinos, this probability is mind-bogglingly small.
How small are we talking?
Well, to give you a sense of scale, a typical solar neutrino, zipping along with a few MeV of energy now, MeV is a unit of energy used in particle physics, would need to travel through about a light year of solid lead.
A light year.
A light year of lead, to have a 50% chance of interacting even once.
Just a 50% chance after a light year of lead. That really puts into perspective just how rarely these things will bump into anything. They're like cosmic ninjas just slipping through everything.
That's a good way to put it.
Okay, so we know they're elusive, but we also mentioned that they come in different flavors.
Yes. Just like there are different types of quarks or charged leptons, there are 3 known flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino.
Electron, muon, tau. Okay.
And each one is associated with its corresponding charged lepton, the electron, the muon, and the tau particle. So it's like a family of these near-invisible particles, each with its own identity linked to a more familiar particle.
So it's like a little family of near-invisible particles. And I remember reading something about them changing their identities oscillating.
That's right. This is the phenomenon of neutrino oscillations. It's one of those fascinating discoveries in neutrino physics.
Okay.
As neutrinos travel, they can spontaneously morph from one flavor into another.
Spontaneous.
Yeah. For example, an electron neutrino born in the sun can transform into a muon neutrino or a tau neutrino by the time it reaches Earth.
That sounds like something straight out of science fiction. So one moment it's an electron neutrino, the next it's something else. How does that even happen?
Well, the full explanation involves quantum mechanics, but the key takeaway is that this flavor changing is only possible if neutrinos have mass.
Ah, okay. The changing proves the mass.
Exactly. The fact that we observe these oscillations, confirmed by landmark experiments like Super Kamiokande in Japan
Super K.
and the Sudbury Neutrino Observatory in Canada, SNO, that's direct evidence that neutrinos are not massless. And it also tells us that the individual lepton flavors aren't conserved in all interactions.
So the rules we thought we had about these categories aren't quite right?
That's it. So having these different flavors isn't just about a particle zoo. It has profound implications for our understanding of fundamental particle categories and the very nature of mass.
Mind blown. Okay, so these shape-shifting, nearly undetectable particles are out there. Where do they even come from? It can't just be rogue neutrinos floating around, can it?
Not at all. No. Neutrinos are actually produced in a vast array of processes, both natural and artificial.
Okay.
One of the biggest sources, as we hinted at, is our own sun.
Right, the sun.
The nuclear fusion reactions happening in its core generate enormous numbers of electron neutrinos. These solar neutrinos are actually what Raymond Davis Jr. famously detected in his pioneering experiments.
Right, those early experiments we'll get to in a bit. What other natural sources are there?
We also have atmospheric neutrinos. These are created when high-energy cosmic rays from space collide with atomic nuclei in the Earth's atmosphere.
Cosmic rays hitting the air.
Yep. These collisions produce a shower of secondary particles, many of which decay and produce neutrinos, primarily muon and electron neutrinos.
Okay.
And there are geoneutrinos.
Like from the Earth.
Exactly. Produced from the radioactive decay of elements like uranium and thorium deep within the Earth. Studying these can actually give us insights into our planet's interior composition and heat.
Radioactive decay inside the Earth producing neutrinos. That's wild. And are there any other big cosmic neutrino factories?
Absolutely. When massive stars reach the end of their lives and undergo a core collapse supernova,
Kaboom.
a huge kaboom, yeah, they release an absolutely staggering number of neutrinos of all flavors. It's estimated that about 99% of the energy of the collapse is emitted as neutrinos.
99%. Just in neutrinos.
Just in neutrinos. The detection of neutrinos from supernova 1987A was a landmark event, providing crucial confirmation of our understanding of these stellar explosions.
I remember hearing about that one.
And beyond our galaxy, we believe that extremely energetic astrophysical phenomena like active galactic nuclei, AGNs,
Supermassive black holes feeding.
right, and gamma ray bursts, GRBs, these incredibly powerful explosions.
Yeah.
We think they're also sources of very high-energy cosmic neutrinos.
So from the quiet reactions in the Earth's core to the violent death of stars, neutrinos are being churned out all over the place. What about human-made sources? Do we make them?
Yes, we produce them too. Nuclear reactors, for example, generate a significant flux of electron antineutrinos as a byproduct of nuclear fission.
Antineutrinos, the antimatter version.
That's right. These reactor neutrinos have been invaluable for studying neutrino properties, especially oscillations.
Yeah.
We can also create beams of neutrinos in particle accelerators by smashing high-energy protons into targets. The resulting particles decay and produce well-defined beams of neutrinos that can be directed towards detectors hundreds of miles away.
Aiming beams of neutrinos.
Wow, okay, so the universe is practically swimming in neutrinos from all sorts of sources. But if they're so hard to interact with, how on earth do we actually detect them? This must involve some serious scientific wizardry.
It absolutely does. Detecting neutrinos requires pushing the boundaries of technology. You need, well, three main things.
Okay.
Massive detectors to increase the chances of a rare interaction.
Rigor target.
Right. Incredibly low background environments to avoid being swamped by other signals.
Peace and quiet.
And extremely sensitive technology to pick up the faint traces of a neutrino interaction. Often, these detectors are located deep underground to shield them from cosmic rays that can mimic neutrino signals. Underground neutrino observatories. That sounds like something out of a Bond film. So let's talk about these ingenious detection methods. You mentioned some historical ones like radiochemical methods.
Yes, the pioneering work of Raymond Davis Jr. and his homestake experiment. He used a massive tank filled with perchloroethylene.
Isn't that cleaning fluid?
It is, yes. Dry cleaning fluid, basically.
Yep.
Located deep in a gold mine in South Dakota.
Okay.
The idea was that occasionally a solar electron neutrino would interact with a chlorine nucleus in the fluid, transforming it into a radioactive argon atom.
A chlorine atom becomes an argon atom.
A radioactive isotope of argon, yes. Over several months, maybe a few dozen argon atoms would be produced in this enormous tank, like 600 tons of fluid.
A few dozen atoms in months.
Yeah. And Davis and his team developed this really clever method to chemically extract and count these tiny numbers of radioactive atoms. It was an incredibly challenging and innovative experiment that gave us the first glimpse of the solar neutrino flux.
Talk about finding a needle in a haystack and proving it was there without actually seeing the neutrino itself.
Exactly. It was indirect, but groundbreaking.
Okay, so that's the historical approach. What about more modern techniques? I've heard of these huge water tanks that can see neutrinos.
You're thinking of water Cherenkov detectors, like Super Kamiokande in Japan and IceCube at the South Pole.
Right.
These detectors use vast quantities of ultra-pure water. In the case of Super K, it's about 50,000 tons.
50,000 tons of water.
Ultra-pure. When a neutrino interacts with an electron or a nucleus in the water, it can produce a charged particle, say, an electron or a muon, that travels faster than the speed of light in water.
Faster than light in water, but not in a vacuum.
Correct. And when this happens, the charged particle emits something called Cherenkov radiation. It's essentially an optical shock wave, like a sonic boom, but with light. It manifests as a faint blue glow.
So the interaction creates a tiny flash of light in the vast darkness, like a light boom.
Precisely. And the detector is lined with thousands of highly sensitive photomultiplier tubes, PMTs, which are like incredibly sensitive light detectors. They can detect these faint flashes of light. By analyzing the pattern, the intensity, and the timing of the light hitting these tubes, scientists can reconstruct information about the incoming neutrino, its direction, its energy, and even its flavor, because electrons and muons create slightly different light patterns.
Wow, reading the light pattern tells you all that.
It does. And IceCube takes this concept to an even larger scale, using a cubic kilometer of Antarctic ice as its detection medium.
Ice instead of water.
Yep. The ice is naturally very clear, and they embed strings of these PMTs deep within it. IceCube is designed to study very high-energy astrophysical neutrinos, the ones from those AGNs and GRBs we mentioned. The sheer scale allows it to capture incredibly rare interactions from the highest energy cosmic events.
A cubic kilometer of ice with light sensors, that's on a whole other level.
Yeah.
What are some other detection techniques? You mentioned scintillation detectors.
Yes. Scintillation detectors use materials, often special liquids, or sometimes plastics, that emit a flash of light, a scintillation, when a charged particle passes through them.
So a direct flash, not a shockwave.
Right, a more immediate flash of light. These light flashes are then picked up by photomultiplier tubes, similar to Cherenkov detectors. Experiments like CAMLAND in Japan and Borexino in Italy use large volumes of liquid scintillator.
Okay.
They are particularly well suited for studying lower energy neutrinos, like those from nuclear reactors in the sun, with really high precision. They can often measure the neutrino energy more precisely than water Cherenkov detectors, and sometimes distinguish between different types of neutrino interactions based on the timing profile of the light bulbs.
So different materials, different light signatures, all helping to piece together the puzzle of these elusive particles. And the last technique you mentioned was liquid argon time projection chambers. That sounds very high-tech.
It is. It's a newer but very powerful technique. Liquid argon time projection chambers, or LRTPCs, offer incredibly detailed photographic images of neutrino interactions.
Photographic, like a picture.
Almost, yeah. They use a large volume of super pure liquid argon as the target material. When a neutrino interacts, it produces charged particles that fly through the argon, ionizing the argon atoms along their path, knocking off electrons.
Okay, leaving a trail of electrons.
Exactly. These ionization electrons then drift in a carefully controlled electric field towards planes of very fine wires at the edges of the detector.
Drifting electrons.
Right. By measuring the arrival time and the amount of charge deposited on these wires, scientists can reconstruct the three-dimensional tracks of the charged particles with remarkable spatial resolution. You get this beautiful, clear picture of the neutrino interaction, almost like seeing the event unfold in 3D.
That sounds incredibly precise.
It is. Experiments like Microboon at Fermilab have used this. And the future Deep Underground Neutrino Experiment, DUNE, will use massive RTPCs. It's seen as a key technology for the future of neutrino physics.
It's amazing how much effort and ingenuity goes into building these massive, ultra-sensitive detectors just to catch a glimpse of something that barely interacts with anything. So with all this difficulty, why bother? Why is it so crucial that we dedicate so much time and resources to studying these elusive neutrinos?
Because despite their elusiveness, neutrinos hold a wealth of information about some of the most fundamental processes in the universe.
Okay, like what?
For example, by studying solar neutrinos, we can directly probe the nuclear fusion reactions happening deep within the sun's core, confirming our models of how stars shine. It's like having a probe inside the sun.
A direct look inside.
Exactly. Neutrinos from supernovae give us a unique window into the cataclysmic collapse of massive stars and the formation of neutron stars or black holes, seeing how 99% of the energy escapes.
Essential for understanding those explosions.
Absolutely.
Yeah.
And as we discussed, the fact that neutrinos oscillate and have mass was the first concrete experimental evidence that the standard model of particle physics, as originally formulated, was incomplete. It pointed toward the need for new physics.
A crack in the standard model.
A very significant one. They are truly messengers from the depths of stars and the most violent cosmic events, carrying information that light can't.
So they're like messengers from the heart of stars and other extreme environments?
Precisely. Furthermore, studying neutrinos can help us understand some of the biggest mysteries in cosmology, like the matter-antimatter asymmetry. Why is there more matter than antimatter in the universe?
The big question.
It might be related to subtle differences in how neutrinos and antineutrinos behave, something called CP violation in the lepton sector.
Okay, deep stuff.
Determining the absolute mass scale of neutrinos is also a major open question, with implications for how structure formed in the early universe. And finally, these high-energy cosmic neutrinos are opening up a whole new field neutrino astronomy, allowing us to study the most energetic astrophysical objects in a way we couldn't before.
A whole new window on the universe.
Exactly. So these ghost-like particles are carrying some pretty heavy secrets of the universe, and deciphering them is key to a deeper understanding of reality.
It sounds like these ghost-like particles are actually carrying some pretty heavy secrets of the universe. Now, you mentioned that elusiveness isn't just a neutrino thing. Are there other known standard model particles that give us a hard time?
Yes. While neutrinos are the poster child for elusiveness due to their weak interactions, other particles can be difficult to study for different reasons, often related to how rarely they do certain things.
Okay, not just hard to see, but hard to catch doing something specific.
Exactly. One example is through their exceedingly rare decay processes. Particles like kaons, B-mesons, and muons. They're produced relatively frequently in high-energy physics experiments. We can make lots of them.
Right.
However, some of their decay modes, ways they break down into other particles, are predicted by the standard model to be incredibly rare, sometimes occurring only once in billions or even trillions of decays.
1 in a trillion.
Or rarer. So we might look at trillions of particle interactions just to find a handful of these specific rare decays.
Why are these rare decays so interesting if they hardly ever happen?
Because observing these rare decays, like a kaon decaying into a pion and 2 neutrinos, or a B-meson decaying into 2 muons, it requires sifting through absolutely enormous data sets
Huge amounts of data.
and developing incredibly sophisticated techniques to reject background noise from more common processes that might look similar. The key thing is, these rare decays are often very sensitive to subtle quantum effects,
Okay.
and they can be influenced by new, undiscovered particles or forces that aren't part of the standard model.
Okay.
These hypothetical new particles could pop into existence for a fleeting moment during the decay process and slightly change its probability.
Ah, so they act like tiny windows into physics beyond what we know.
Exactly. So the observation of a rare decay at a rate different from the standard model prediction could be a very strong sign of new physics at play.
So it's like looking for a very specific grain of sand on a massive beach, and if you find one that looks a little different, it could be a huge discovery.
Precisely. That's a great analogy. Another area where elusiveness comes into play is in making extremely precise measurements of fundamental properties of known particles.
Like measuring something we already know exists, but measuring it really well.
Exactly. For instance, trying to measure the anomalous magnetic dipole moment of the muon, how much it wobbles in a magnetic field with extremely high accuracy, or searching for a tiny electric dipole moment, EDM, in fundamental particles like the neutron or the electron.
Electric dipole moment, like a separation of charge within the particle.
Sort of, yeah. The standard model predicts these EDMs should be incredibly tiny, practically zero. Finding a non-zero EDM would be a huge deal
Why?
because it would violate certain fundamental symmetries and strongly point towards new physics. These particles, the muon, the neutron, they're well established, but these measurements probe very subtle quantum mechanical effects and require incredibly precise and stable experimental conditions.
More incredibly difficult experiments.
You got it. And again, any tiny deviation from the standard model's predictions could hint at new particles or forces at play. So elusiveness isn't just about the particle being hard to detect in the first place, but also about the challenge of observing specific, very rare behaviors or measuring fundamental properties with extreme precision.
It seems like the universe often whispers its secrets rather than shouting them. So looking back at our pursuit of these elusive particles, particularly neutrinos, what are some of the big lessons we've learned along the way?
One key lesson is certainly the immense power of indirect evidence and theoretical prediction. Pauli's initial idea of the neutrino was purely theoretical.
Right, to balance the books on energy.
Exactly. It was a theoretical necessity to explain an experimental puzzle. It took decades to confirm its existence directly, but the theory guided the search. That's powerful.
Very leading experiment.
We've also learned about the crucial role of innovation in scientific instrumentation. The need to detect these faint signals has driven incredible advancements in detector technology, from huge underground tanks to supersensitive light detectors, ultra-pure materials, sophisticated electronics, complex data analysis.
Pushing the tech frontier.
Absolutely. The very act of trying to see the unseen pushes the boundaries of what's technologically possible.
And I imagine a lot of patience is involved, too. You mentioned that 26-year gap.
Oh, absolutely. Patience and persistence are key. These experiments often run for many years, even decades. They require sustained effort from large international collaborations involving hundreds, sometimes thousands, of scientists.
Long-term vision.
Definitely. And perhaps one of the most profound lessons is that seemingly small discrepancies or puzzles, like the initial deficit in the number of solar neutrinos we observed, the famous solar neutrino problem.
Where they weren't finding enough neutrinos from the sun.
Right. It seemed like a small problem initially, maybe an issue with the experiments or our understanding of the sun, but that puzzle actually led to a major breakthrough.
Which was?
The discovery of neutrino oscillations, and consequently, neutrino mass. It fundamentally changed our picture of particle physics, proving the standard model needed revision. So sometimes the biggest discoveries come from investigating the small things that don't quite fit.
So even the things we don't see or barely see can lead to huge revelations. This has been a fascinating deep dive into the world of these elusive particles. To recap, neutrinos, despite being fundamental, are incredibly hard to pin down due to their lack of charge, tiny mass, and preference for only weakly interacting.
Yeah, they just don't like to talk to other matter much.
Yet the remarkable ingenuity of scientists has led to the development of incredible detection techniques. Giant tanks of water or cleaning fluid, cubic kilometers of ice, vats of liquid argon that allow us to study them.
It's truly amazing what's been achieved.
And as we've seen, the effort is more than worth it. Studying these elusive particles and the subtle aspects of even well-known particles through rare decays or precision measurements is absolutely vital for pushing the boundaries of our understanding.
Right. It's how we probe the universe, from the workings of the sun to the explosions of stars, and how we search for potentially revolutionary new physics beyond our current theories.
It really makes you wonder, doesn't it? Consider how many other silent or weakly interacting phenomena might be occurring all around us right now that we are only just beginning to perceive, or perhaps haven't even conceived of yet.
That's a great thought. Dark matter, dark energy, perhaps other things too.
The universe clearly holds many secrets, and it often takes the most persistent and innovative approaches to finally uncover them.